What's the secret?
Relax.
But how could you relax?
That's the secret.
Oh, now you're about to get hit by 300 nasty pounds of Derek Thomas. I mean, bones are in danger of being broken. Limbs might be torn off, and you're telling me you relax?
Right.
No way.
Way.
Relax.
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 Sports Figures. Put your brain in the game.
You might think I just kicked that ball, but I did something way cooler than that. I changed the ball's momentum. Now, sitting here on the tee, the ball's momentum is 0. It has mass, but no velocity. It's just sitting here. Now it has momentum. It's moving. It has mass and velocity. So, how did I change its momentum? To change something's momentum, we have to add a force. You might think that's a kick, but it's not. It's really an impulse. In physics, we describe the force that changes something's momentum with the word impulse. You know the word impulse, right? It's when you do something on the spur of the moment without giving it much thought. Like when you buy all the stuff next to the cash register. That's called impulse buying. Oh, I love these. So impulse has to do with time. In physics, it's the same thing. A force that happens over a finite period of time. Time is what makes a force an impulse. How long a force acts for.
So, Napoleon, you take a lot of hard hits out there.
Oh, yes, definitely, on a game-to-game basis.
When you get hit, when you get crushed by someone like Derek Thomas, how do you guys just spring back up? I mean, how do you not break every bone in your body?
Well, first of all, we have pads on, definitely, and spending a lot of time in the off-season getting physically fit and getting prepared for the pounding that we're about to take during the year.
Another way a running back could lessen the force of a tackle is to relax. That seems weird, right? I mean, how could relaxing when you're about to get tackled help? It seems to me if I were going to get hit by Derek Thomas, I'd want to tense up my muscles when I got tackled. So, why relax?
I guess it'll be like your body bends when it gets hit, so it doesn't hurt as much.
Yeah, and something that's stiff breaks easier than something that bends. You're more flexible.
What if I told you it has to do with time?
Time?
Time. What if I were to jump from this diving board and land on the concrete down below? But what if I were to jump from up here and land in the water?
We know that the watermelon had momentum when we dropped it. And we know that both watermelons had the same momentum because they had the same mass and they were dropped from exactly the same height. So why did one watermelon splat and the other survive? Woo! Now you might think the reason I can jump from way up there and land safely in the water is because water is softer than concrete. And that's sort of right. But the reason it really works is time. When the watermelon hit the concrete, it had lots of momentum. After it hit the concrete, its momentum was 0. It stopped. Its momentum was affected by a force, the resistance of the concrete. When the watermelon hit the water, it had the same amount of momentum. And after it hit the water, its momentum was 0. It stopped. Its momentum was also affected by an outside force, the resistance of the water. The change in momentum was exactly the same. Because of that, we could say that both watermelons were affected by a force, and forces change momentum. But obviously, the forces affected the watermelons a little differently.
The difference was that it took longer for the watermelon to stop in the water.
Right, so we can't just look at the presence of force, we have to look at force and time. And Napoleon, force and time are?
Impulse.
Correct. The difference is how long it took for the momentum to change. And the time it takes for a force to change something's momentum is an impulse, right? Remember what we said? When a force changes something's momentum over a finite period of time, it's an impulse. No momentum. Impulse. Momentum. One of the things we know about momentum is that it has both magnitude and direction. So a change in direction is a change in momentum too. Let's go to the sports figures blackboard and take a look.
An impulse doesn't necessarily have to stop a player like a tackle. Often we'll see a running back bounce off another player, changing his direction. That's an impulse too. Here we see Kaufman take a shot, but it doesn't stop him. What it does is change his direction. If his direction is changed, you know his momentum is changed. That's impulse at work right there. What this means is that we can figure out impulse in more than one dimension. A force for a finite period of time. It can stop you or change your direction, but it's always an impulse. I'm Mark Malone for the Sports Figures Blackboard.
So the impulse was the same for both watermelons, but the force was greater for one because the time was so small. The difference in time is what smashes the watermelon.
Or not. Look how long it took for the water to stop the downward momentum.
The same thing happens when we give momentum to an object. Now, when we kick a football, we're adding a lot of force over a short period of time. That's an impulse.
But what would happen if we give it the same amount of force over a longer time?
Yeah, the kick is sort of like the concrete, but what's the same as the water?
Well, we can figure it out like this. First, we'll have Veronica kick the football.
Look at the equation for impulse. Force times time equals the change in momentum. We get the change in momentum by subtracting the momentum after the impulse from the momentum before the impulse. We know the football's momentum before the kick is 0 because it's not moving. After Veronica kicks it, we figure out the momentum by multiplying mass and velocity. Let's say her kick resulted in a momentum of 6 meters per second. So that's our change in momentum, 6. Using high-speed photography, we can find how long Veronica's foot was in contact with the ball. About 8/1000ths of a second, 8 milliseconds. That's our time. To solve for F, we just divide the momentum by the time to get a force of 750 newtons.
Okay, so Veronica's kick had a force of 750 newtons. Now, let's see what happens if we change the ball's momentum with the same force over a different time. We'll have Mohammed here throw the ball.
Again, the ball starts with the momentum of 0, and when Mohammed throws it, the ball has the same velocity and obviously the same mass. Mohammed's throw gives it the same momentum as Veronica's kick, 6 meters per second. But the big difference is this. When we figure out the time during which Mohammed applied force to the ball, we find that it's much slower. His hand was moving forward with the ball for half a second. We solve for F again and get 12 newtons of force.
Whoa, that was way different. It wasn't even close. I mean, your force is a whopping 750 newtons, but yours is only 12.
Yeah, but the ball went the same speed.
The change in momentum was the same.
Right, but you applied a little force over a longer period of time, and you gave a lot of force over a short period of time to get the same result.
There's lots of ways to get an impulse of 6 meters per second. A large force in a short time or a small force in a long time.
Oh. That's why in sports, they always tell you to follow through when you hit the ball. Because the longer you make contact with the ball, the bigger the impulse and the bigger the momentum change. That brings us to football pads. Now, these pads are filled with soft, cushy foam. There's foam in this helmet, foam under the shoulder pads. These are hip pads, and these are thigh pads, all foam. And foam is all about time.
One of the things football pads do is increase the impact time when you get hit. The foam compresses, and that takes time. Just like the water, the force is less because it changes your momentum more slowly. Oh. Look at the way an airbag works. What the airbag does is add time to the impact. More time, less force.
The principle of force times time equals change in momentum is around us every day. You see, what a shock absorber really does is extend the amount of time of the impact. More time, less force. Okay, Napoleon, so now we know why you're supposed to relax when you get hit.
Right, it works like this. Hold up your hand and hold it really stiff.
Okay? Oh, yeah.
Now hold up your hand and relax it.
Okay. Wow, that didn't hurt at all.
See, now when you get hit and your body's relaxed, your body gives way with the hit.
Right, and the more time it takes to change the momentum, the less the force.
Right. Haven't you ever heard the expression roll with the punches?
Yeah, sure. Now, it doesn't seem like you can change the time of impact much by relaxing, but we saw with kicking the ball and throwing the ball that every fraction of a second has a big effect on force.
Yeah, when you're getting hit by Derek Thomas, you take all you can get.
Okay, guys, so what did we learn?
That to change something's momentum, we need an impulse.
An impulse is a force for a finite period of time. And the time that it takes for momentum to change determines the force.
And if the momentum changes really fast, then the force is going to be greater.
All right, very cool. Let's play some football. Okay. So while it might seem like tightening up your muscles when you get tackled is the way to go, relaxing is really the key.
I told you.
Well, I'd like to thank Napoleon Kaufman and the Oakland Raiders.
I got momentum.
And of course our students, Marquez, Mohammed, Veronica, Asha, and Kong. Officer Steve Lovell of the Oakland Police Department for helping us out today on ESPN Sports Figures Relaxing with Him. Running with Momentum.